Hello everyone. So I will probably write this out, but if you're watching the video, I'll give you a quick explanation of what I decided to do ever since getting the information about how they're going to do the AP test. So hopefully you read that article. I'm going to go ahead and start reviewing. Now if you are interested in finishing Chapter 7, I will link the Khan Academy videos, and so if you have the time, I would highly recommend going ahead and finishing it just for your own knowledge, and if you go to college and have to take a calculus course. Sorry if you can hear my dog click-clacking again. But after getting y'all's input, I decided it'd be best if we go ahead and start reviewing. So what it's going to look like is today, every chapter is going to have about a one-page front and back, just quick review of just the main topics. And so hopefully you still have your notes, and you can go back. If we go over something that you're like, I don't really remember that, you can go back and look at your notes. And I will also post Khan Academy videos that correlate if you need a more lengthy explanation. But these videos are not to completely explain it, but more be just a refresher. But as always, if you need me to go over anything more, please let me know and I can do an additional video over a certain topic. So what we're going to do is today we're going to do chapters 1 and 2 together. And then Wednesday we'll do related rates. Friday, now I'm forgetting because I don't have it in front of me, but basically we'll either do 1 or 2 chapters every Monday, Wednesday, Friday, just depending on the length of it. And so by the end of 2 weeks, we should have reviewed every topic. Okay, so let's go ahead and jump into chapter 1. And so if you want, it might be beneficial for you to get your chapter 1 notes out, and you can have them side by side and look over anything as we go over it if you need the additional examples or explanations. So chapter 1 was over limits. So the first thing is just saying, what does the limit as x approaches 3 of f of x equals 7 mean? So I'm just going to basically write out what I just said in words. So when you see that, it means as x approaches 3 from the right and left, y approaches 7. So notice we avoid the word equals because it doesn't have to necessarily equal. It could be a whole. So let's draw a visual of what that's saying. So if you have a graph, and if this is f of x, then that means at 3, it doesn't necessarily have to equal 7, but it has to approach that y value of 7. So it could be a whole right here, and that whole, the y value is 7. So technically f of x doesn't equal 7 at 3, but it is approaching. So from the right and the left, you're getting very close to 7. Now it can equal. I could fill in that hole if I wanted to, but I don't have to for the limit to equal 7. Right? And so for the limit to exist, you have to approach the same y value from the right and the left. So what does that mean is it can't be a jump. Right? A limit can exist at a hole, but it can't exist at a jump. So a left-hand limit would, y'all remember the notation, is as x approaches 3, and if you want to say from the left, you put a little negative of f of x. Now I'm going to change this one up and we'll draw another picture. Let's say they said that equals 4, and then they said the right-hand limit as x approaches 3 from the right, so you put a little plus sign, of f of x equals 10. So what would that look like is at 3, we'll put 4 here, 10 up here. We don't know what the function's doing anywhere else, but an example could be that as you come from the left side, you approach the y value 4. Now, so I'm coming right here, and as I get to 3, I should be at 4, and then that could be a closed circle or an open circle. It doesn't matter. I'll make it closed because I was already right there. And then when you approach 3 coming from the right side, so I could be either coming up or down, we don't know what it's doing, but when it gets to 3 from the right side, you should be reaching the y value 10. And again, that could be an open or a closed circle. They could both be open, both be closed. We don't know that, but we just know that from the left, we stopped at the y value 4, and at the right side, we stopped at the y value 10. Okay, so that's the notation we use and what it looks like graphically. So here, the limit, and it's going like this, oops. The limit as x approaches just 3, no right or left sign, would not exist because the left and the right are different. So we would say a D and E does not exist. So then, if we're doing limits algebraically, you always plug in the number. X is approaching, which in this case they use C. And so what is that? That's your direct substitution, right? You always do direct sub first. So you plug in your C, and so let's say when you plug it in that's just a number. If it's any old number, then you're done. That's your answer. That's the limit. Let's say you plug in your C, and you get some number divided by 0. Any number divided by 0 is undefined. So what it tells you is that you have a vertical asymptote at x equals c. So what does that mean for the limit? Is that the limit as x approaches c of f of x, if it's approaching a vertical asymptote, it's either going to be infinity, negative infinity, or if the right and left side are different, it would be D and E. And we'll kind of review in a little bit what you would do to test that. Remember, you pick a number really close. And then the last scenario is if you get 0 over 0. So that, hopefully you know, is your indeterminate form. So what does that mean? It means you either need to do more work. Oops, I don't know what I was about to write. So what is that? That could be factoring or multiplying by a conjugate, or you could be doing long division. And you could go back and look at your examples in your chapter 1 notes. Or if you don't know what more work to do, in chapter 5 we learned L'Hopital's rule. So if you're not sure what more work to do, I would go ahead and just do L'Hopital's rule. So here's an example. Well, real quick. Notice we didn't talk about 0 over a number. That's just 0. That would fall under this category. Slash 0 divided by a number is just 0. So it's okay to have 0 on top. So in this example, we look at here, we always plug in our number first, which you could do this part in your head if you want, or you can go over to I would go over to the side and test it out. But I'm going to do 4 minus 4 on top, so that I know that would be 0, and then 4 squared is 16 minus 16 is 0, so I can see that I would have my indeterminate form. So I have a choice. I can either do more work or L'Hopital's, which I'm actually going to do L'Hopital's down here, so I'm going to do more work here. So when I see that, I would first try to factor. So I know the top I can't factor, but the bottom is difference of squares. So you rewrite your limit. Always write your limit until you plug in your number. I'm going to keep the top the same in this case. And this is difference of squares. So the square root of 16 is 4. So it's x minus 4 and x plus 4. So then I can see that these cancel. And what does that mean when those cancel? Well, let's finish the problem, and then I'll kind of break down why this works. So when those cancel, you can rewrite it. So that would equal the limit as x approaches 4. What is left on top is a 1, right? Because that's like that whole factor cancels, so you're left with just a coefficient 1 over x plus 4. Now you try to plug it in, which we can see it'll work. It'll be 1 over 4 plus 4, so 1 over 8. So I know I've had some questions in the past about why this works, is if you relate it back to pre-cal. When a factor cancels, that gives you a whole, right? So we have a whole at x equals 4, the solution to that factor that canceled. So if you notice, that's what your limit's approaching. So we're talking about this whole here. So this is the y value of that whole. So that's why it didn't work at first, because it's technically your function's undefined at a whole, but the limit, the y value of the whole, is 1/8. So if we look at this next one, I really should have done one without a graph, but hopefully this just makes it connect, but we'll talk about what you would do if you didn't have the graph. So you first think, I'm going to plug this in, and you should know what 1 over x looks like, but if you didn't, I would plug it in and I would see that I would get 1 over 0, which I know that tells me then that there's a VA at x equals 0. Now that's not your answer, but as soon as you determine that, you know that your answer should either be negative infinity, infinity, or if from the right and the left it's opposite, then it would be does not exist. But you can look at this graph and see, so this is your vertical asymptote. As we come from the right, it's approaching positive infinity. It's going up forever. As we approach it from the left, we're going down forever. So since it's not the same, you have to say that it does not exist. So we know the answer, but let's say you didn't have the picture. What would you do? Well, we would have to test each side. So I would first do approaches from the right. So how do you know that's going to be infinity or negative infinity? As you go over to the side and you pick a number really close to 0 on the right side of 0. So I wouldn't pick 1, I would get even closer, like 0.1. Get really close, and if I think about plugging in that number, if I plug in 0.1, is that a positive or a negative? That's a positive. So because it's a positive, this limit's going to be positive infinity. Okay, this only works when you already determine that it's a vertical asymptote. And then you can do the left side. This is at the end of your Unit 1 notes also if you wanted more examples. So then we're going to plug in a really close number to 0 on the left side. So that would be like a negative number, negative 0.1. So if I plug it into my function, I get 1 over negative 0.1, which would be a negative number. So I know that that would be approaching negative infinity on the left side. So always, in this case, you probably could have picked a number farther away and it would have still worked, but on other problems, if you don't pick a number pretty close, like a decimal type number, your number might be off and get you the wrong side. So we can see that those are opposite, so we know the official answer, because it didn't ask for the right or the left. It just asked as you approach 0. If the right and the left are different, then it is D in E. I just noticed right here I forgot to write my function, which is bad. It should be 1 over x. Okay, so then let's do a quick L'Hopital's review. So L'Hopital's is whenever you have a limit indeterminate form, which could be 0 over 0, or it could also be infinity over infinity, or if there's a negative in there, it still works. You can use L'Hopital's rule. So remember, you have to take the derivative of the top and the derivative of the bottom separately. It is not quotient rule. Okay? You're just doing the derivative of the top and the derivative of the bottom. This is in chapter 5 if you need to go look at these examples. So when we're going to do it here, remember you first you can either write it down or think about it in your head. You can see that it's 0 over 0. So if you didn't want to do it how we did it here and you want to do L'Hopital's rule, remember if it is a free response, not multiple choice but a free response, you would need to first go over to the side and you would need to write out that the top limit 0 and the bottom limit 0 separate. I hope I have enough room. These markers are starting to bleed more. So of just the top, I can see that if I plug in 4, that would be 0. And then do the bottom one, which is x squared minus 16. If I plug in 4, that would also be 4 squared 16 minus 16 be 0. So because those are both 0, and you might want, if you had more room, you could write this out like in order. Then you would go back and you would say by L'Hopital's rule, which I'm going to abbreviate for the sake of room, this original limit will equal the limit as x approaches 4 of the derivative of the top, which would just be 1, over the derivative of the bottom, which would be 2x. Now you redo direct substitution, 1 over 2 times 4 is 8. You can see that's the same answer as above. So here's another one, and again, at any point you can pause these videos and do it on your own or skip ahead if you already know this topic. But here's another one. So we see if I plug in 0, I know e to the power of 0 is 1. So 1 minus 1 would get me 0 on top. Same thing on bottom. This would still be e to the power of 0, which is 1 minus 1 is 0. So I'm going to try L'Hopital's rule. So I'm going to do the limit as x approaches 0 at the top. Which would be e to the 2 times 0 minus 1, which would be e to the 0 minus 1, which would be 1 minus 1, which is 0. Same thing for the bottom. So I'm going to say by L'Hopital's rule, I can set the original limit equal to the limit as x approaches 0 of the derivative at the top, which you can do this out of order if you're comfortable. Remember, the derivative of e, it stays the same. You got to do times the derivative of the exponent, so times 2. The derivative of negative 1 is 0. Over the bottom is e to the power of x, which would just stay the same. This is blending in with my other work. So you can do direct substitution. So we have e to the power of 2 times 0 times 2 over e to the 0. So e to the 2 times 0 is e to the 0, which is 1, times 2 over e to the 0 is 1, so that's just 2. That got kind of smushed, but I hope you can follow. Okay. So on the back is a review of horizontal asymptotes and limits at infinity. So horizontal asymptotes, this is taking longer than I thought, is also known as the end behavior. It's what it's what your graph is doing forever to the right or forever to the left, right? It's talking about what is the graph doing as x goes forever to the right, goes to positive infinity, or what is the graph doing as it goes forever to the left, negative infinity. So what it's going to do is it's either going to go up forever, down forever, or approach a horizontal asymptote. So that's where we use these Bobo Bottom Eats DC. So that, I'm not going to write all this out to save time. You can look, you should be able to look in your notes. I want to say this is in a different chapter too, now I can't remember. But you can pause the video and write it yourself. Bigger on bottom, then it's going to be y equals 0. Bigger on top is none, which we'll talk about what you would do for that. And then if the exponents are the same, you divide the coefficients. So that is talking about horizontal asymptotes. So how does that line up with limits? So we're going to look here. First it says find the horizontal asymptote. So you look at the degree. You only care about the largest exponent. We can see it's bigger on top, so that would be none. So that means it doesn't have a horizontal asymptote. Now that's probably not what on your AP calculus test it's going to ask. It's probably going to say, it says find the infinite limit. So find the limit as x approaches infinity of this function, which I could have actually probably wrote the function because it would make more sense. So when, this only applies if it's x approaches infinity or negative infinity down here, is you can just look at the biggest coefficient, right? So we're going to know that that limit is going to be equivalent to whatever just the biggest coefficient on top over the biggest, why am I saying coefficient? Degree, my bad. The biggest degree on top over the biggest degree on bottom. All the other stuff we don't care about. So now if you can either, or you can just always think about now plugging in infinity. Or simplifying this first, actually, would probably be best. So x squared divided by x would leave you with just x. So now if you think about plugging in infinity, the limit equals infinity. So same thing here. If we first think about horizontal asymptote, so if it's none, or horizontal asymptote, the answer is going to end up being infinity or negative infinity. Here, the exponents are the same, so you divide the coefficients. So it's 2 over 1, so your horizontal asymptote is what? 2. So then what does that mean for the limit? As x approaches infinity of, instead of writing f of x, I'm going to actually write it. I don't know why I did that the first time. So again, if you're approaching infinity or negative infinity, you can cross off everything but the largest terms on top. So then you're left with 2x squared over x squared. So then you notice, because these are the same, they're going to cross off, and you're going to be left with just the coefficients. So then that equals 2 over 1, which is 2. So you notice those are the same. Okay, last one is, if you compare the degrees, it's bigger on bottom, so we know it's y equals 0 because of Bobo. So what does that mean for the limit? If it's approaching infinity, let's see if it's going to be the same if we use this method, where you cross off every term except the largest on bottom and the largest on top, which I circled those backwards. So then that's going to be equivalent to the limit as x over x squared. So if you think about simplifying that, that would simplify to be just 1 over x, right? Because you have one more x on bottom than you do on top. And then if you think about plugging this in, you have 1 over infinity. Any number divided by infinity we know is 0. A number divided by 1 divided by a really big number is going to basically be 0. Which you can see those are the same. So you can think about it through horizontal asymptote, which if it's none, you got to think through, is it infinity or negative infinity? Or you can think through just crossing off everything but the largest term. Sorry, my dog crying, he's being very needy. Okay, so this next part, I think I'm going to skip, because you know how I would actually do these problems is through L'Hopital's rule. So I'm going to write them down, and then I want you to think through how you would get that answer using L'Hopital's rule. So this limit would end up being 1. This limit would be a, and I want you to think about using chain rule when you do L'Hopital's rule on the top. This one would end up being 0, and this one would end up being a over b. There. Okay, so you think through those on your own. If you have any questions about those, let me know. I want to make sure we talk about continuity, because that is an important thing that we haven't touched on in a while. So what does it mean for a function to be continuous? So it's going to be continuous. I'm going to kind of add to this. At x equals c if, so anytime it's talking about continuity, you need to go back. This is the formal definition of continuity. This is what you're trying to prove. That the limit at x approaches c of your function equals the y value of at c. Okay, so what is the definition of continuity? That the limit equals the y value. They're the same. So what is the process of proving that? Would be that you first need to make sure f of c exists, that it's an actual number. Then you need to make sure that the limit exists. So how do you know if a limit exists? What that really goes back to is the right limit equal the left limit. You need to make sure that x approaches c from the left is going to equal the limit as x approaches c from the right, which if you do direct substitution, that is taking care of that. And if those two things exist, they need to be equal, that formal definition that we're looking for. So your third step is to make sure you show that the limit equals the y value. So what does that go back to is then when you break this, when this isn't true, you have a discontinuity, right? So what are your 3 types of discontinuities? A whole, which is considered removable. because you can fill it in with just one point, which a hole, we know what a hole looks like. It's when the graph continues past the hole going in the same. The actual definition is that the limit exists, but it doesn't equal the y value, right? When you approach C from the left and the right, it's the same y value, but the y value doesn't exist there. So you would say the limit as x approaches C of f of x exists in this case, but doesn't equal f of C, because f of C doesn't exist, right? So if it was asking does the limit exist, the answer is yes, but is it asking is it continuous, the answer is no. Those are not the same thing. The next one would be a jump, which this one and the next one are both non-removable, so I'm going to wait to label those together. And what does jump look like? If it was a jump at C, is when the left side and the right side, they jump y values at C. And now those could both be open, both be closed, one be open, one be closed. That part doesn't matter. It's the fact that you have to pick up your pencil and jump to another spot on the graph. So why is this not continuous? Which one of these does it break? Does f of C exist? Yes, this is f of C, the closed circle. Does the limit exist? Is the right side approaching the same y value as the left side? No, right? And that goes back to the beginning of what we just said. So we know this is not continuous because the limit as x approaches C of f of x does not exist. Because of this, the left doesn't equal the right. So if the limit doesn't exist, it can't be continuous. And the last type is a vertical asymptote, which we've already touched on. So these are your two non-removable. So we know what a vertical asymptote looks like. If you have a vertical asymptote at C, it's this imaginary line that your graph goes along forever, but it never touches, so it can either be going up along it, or it could be going down along it, or both sides could be going up, both sides going down. So here, why is this not continuous? Well, f of C doesn't exist, so it breaks that. Technically, the limit doesn't exist, even though these would both be infinity. And so if they don't exist, we'll say it first breaks the first one, f of C, d and e. But if you did want to know the limit, because both these are going up, you would say the limit is infinity, but it still is not continuous. So that is a review over chapter 1. Next will be chapter 2.